Everything you can touch, see, or even breathe, it's all governed by a handful of tiny, invisible rules. So today, we're going deep inside the atom to uncover the fundamental building blocks of chemistry itself.
Really think about it for a second. Yeah, we're made of cells, and those cells are made of molecules, but what if you just keep zooming in, past all of that? What are you really made of at the most basic fundamental level? Well, the answer's right there, at the atomic level. We're going to zoom all the way in to the smallest possible unit of matter that still has the identity of an element, whether it's gold, or oxygen, or the carbon that makes you, you.
All right, let's do it. Let's crack open the atom and meet the tiny particles that literally build our entire world. Okay, so what is an atom, officially? It's the smallest piece of something you can have that still acts like that thing. And here's the absolute key. In its natural state, an atom is neutral. That means its positive and negative charges are perfectly balanced, canceling each other out. This stability is what makes it the perfect building block for, well, everything.
Inside every single atom, you've got three key players. Right at the heart of it, packed into a super dense core called the nucleus, you've got your positive protons and your neutral neutrons. Notice how they each have a relative mass of 1? They're the heavyweights. Then, whizzing around that nucleus in this big cloud are the tiny negative electrons. And just look at their mass. It's practically 0 compared to the guys in the nucleus. And that massive difference in weight, it's going to be super important, trust me.
So now that we know who's in the atom, how in the world do we keep track of them all? Well, chemists came up with a really clever and simple shorthand to describe any atom out there. It's time to learn that language. First up, and this is probably the most important number in all of chemistry, is the atomic number. You can think of it like an atom's social security number. It's the number of protons, and that number alone defines the element. I mean it. 6 protons, always carbon. 8 protons, always oxygen. No exceptions, ever. All right, next up we have the mass number. This one's easy. It's just the total count of the heavy particles, the protons plus the neutrons. Remember how those electrons weigh basically nothing? Well, that's why we can pretty much ignore them when we're talking about an atom's total mass.
So, let's see how this all fits together with a classic, carbon-12. You see the big C? That's our symbol for carbon, obviously. Now, the number at the bottom, 6, is the atomic number. That tells us it has 6 protons. The number up top, 12, is the mass number. So, how do we find the neutrons? All you gotta do is some simple subtraction. Mass number minus atomic number. 12 minus 6 gives us 6 neutrons. See? All the crucial info packed right in there.
Okay, but what happens when that perfect neutral balance of protons and electrons gets messed up? Well, the atom isn't neutral anymore. It becomes an ion, an atom with a net charge. So picture this. It snags an extra electron. Suddenly, it's got more negative stuff than positive stuff. Boom! It's a negative anion. But if it loses an electron, the positive protons are now in the majority, making it a positive cation. And if you ever have trouble keeping that straight, I've got a trick for you. It's a little cheesy, but trust me, it works. A cation is positive. Get it? Like a cat's paw? You are never going to forget that now, especially on an exam. Let's put all this together and solve a little mystery. Imagine we have a particle with 8 protons, 10 neutrons, and 10 electrons. What is it? First things first, who are we dealing with? 8 protons means an atomic number of 8. Pull out your periodic table, and yep, number 8 is oxygen. Okay, next, what's its mass? 8 protons plus 10 neutrons gets us a mass number of 18. Finally, what's its charge? We've got 8 positive protons, but 10 negative electrons, so that's a net charge of -2. And there you have it. We've identified the oxide ion. Case closed.
So, we've nailed down that the proton number for an element is non-negotiable, right? But what about the other parts? Can they change? Oh, absolutely. And this is where it gets really cool.
And that brings us to isotopes. Think of them like different flavors of the same element. They all have the same number of protons, that's what makes them all say carbon, but they have a different number of neutrons. Now, this doesn't change how they react chemically, that's all about the electrons, but it does change their mass, and that can give them different physical properties.
So how do we even know these different flavors exist? This graph here comes from an amazing machine called a mass spectrometer. You can think of it like a super precise sorting machine for atoms. It takes a sample, in this case lead, and flings the atoms around a magnetic curve. The heavier ones don't turn as sharply as the light ones, and what you get is this beautiful fingerprint showing 4 distinct isotopes of lead and telling us exactly how common each one is in nature.
This finally explains that weird decimal number you see for mass on the periodic table.
It's called the relative atomic mass, and it's not a whole number because it's a weighted average. It's just like calculating your final grade in a class, right? The big final exam counts for way more than that first little quiz. The periodic table does the same thing, taking the mass of each isotope and weighting it by how common it is.
Let's run the numbers with bromine to see how it works. In nature, bromine has two main isotopes, one with a mass of 79, the other with a mass of 81. And they're found in almost a perfect 50-50 split. So you just convert the percentages to decimals, multiply each one by its isotope's mass, add them together, and voila! You get 79.90, the exact number you'll find on the periodic table.
Okay, we've been hanging out in the nucleus for a while. It's time to move out into the electron cloud, because the wild world of electrons is where all the action is. We're talking light, color, and the very essence of how atoms connect to each other.
To understand electrons, you have to understand energy. And the main way they interact with it is through light. Now here's the crazy part. Look at that spectrum. All the colors we can see, everything from red to violet, is just this tiny, tiny little slice of the whole thing. It's an enormous range of energy, from powerful gamma rays all the way down to radio waves.
Okay, so here's the deal with electrons and energy boiled down. An electron can absorb a specific packet of energy, a photon, and use it to jump up to a higher energy level. But it can't stay there. It's unstable, so eventually it falls back down. And when it does, it has to release that exact same amount of energy by spitting out a photon of light. And the color of that light? It depends exactly on how big that drop was.
So think about that for a second. If electrons can only make these very specific, fixed jumps between energy levels, what does that mean for the light that an atom actually gives off when it gets energized? It means you don't get a full, continuous rainbow like you do from the sun. Instead, you get a line spectrum. Because the electrons in a hydrogen atom can only make a few specific jumps, they can only emit a few specific colors of light. This pattern of lines is literally an atom's unique fingerprint, written in light. No two elements have the same one. It's completely unforgeable. So let's end with this thought. If every single element has its own unique barcode written in the language of light, just imagine what that means. We can look at the light coming from a star billions of light years away, analyze its spectrum, and know exactly what that star is made of. These atomic fingerprints are literally how we read the chemical story of the entire cosmos.